Our star, the sun, a colossal thermonuclear furnace. Deep within its core, immense pressure fuses hydrogen into helium, unleashing a torrent of energy. For 4.5 billion years, it has blazed, showering our planet with a constant stream of energy. This celestial gift is just a tiny fraction of the sun's total output, yet it's more than enough to power our entire civilization. Countless photons begin an epic 8-minute journey, racing across 93 million miles of empty space. Each one a messenger carrying the sun's power directly to our doorstep. It is the lifeblood of our world. It fuels the winds by warming the atmosphere, drives the great ocean currents, and through photosynthesis allows life itself to flourish, forming the foundation of nearly every ecosystem on Earth. For eons, this direct gift of energy arrived largely unharnessed by humankind. Instead, we dug deep, unearthing the fossilized remains of ancient life. We learned to burn this buried treasure, a ghost of sunlight captured millions of years ago, to power our industrial revolutions. But this reliance on the past came at a great cost. Our consumption of these finite resources has set our world on a precarious path, wrapping the planet in a thickening blanket of carbon. The atmosphere is changing, warming our planet and disrupting the delicate climatic balance that has nurtured us for millennia. Now, we stand at a cosmic crossroads, a pivotal moment in our species' history. We must find a cleaner, more sustainable way to satisfy our insatiable thirst for energy. The answer has been waiting for us all along, shining down from the sky. The challenge is catching this abundant energy efficiently and affordably. It is a test of our ingenuity to build the tools to harness this power directly, using elements forged in long-dead stars like silicon to finally embrace the sun's immediate and endless gift. Silicon became the king of solar for a reason. It's the second most abundant element in Earth's crust, so we'll never run out. It's reliable, and thanks to decades powering the computer revolution, we understand it incredibly well. We've perfected the art of taming it, but that art is a brute force masterpiece. To make a solar cell, you need exceptionally pure silicon, 99.9999% pure. That's a far cry from beach sand, and achieving that purity demands enormous energy. First, the raw silicon is melted in giant furnaces at over 1400 degrees Celsius. Then, using a process perfected for microchips, it's slowly drawn into massive, perfect cylindrical ingots. These perfect crystals are then sliced by diamond wire saws into ultra-thin wafers, each one thinner than a human hair. It's a process of incredible precision, but also waste, as a significant amount of the precious ingot is lost as dust. The entire journey from sand to wafer is meticulous, energy intensive, and slow, an industrial marvel that has scaled globally, but also a fundamental bottleneck. Once you have perfect wafers, the magic begins. They are doped with tiny amounts of other elements, like phosphorus on one side and boron on the other. This creates two distinct layers, one with a surplus of electrons and one with a deficit. Where these two layers meet, they form a p-n junction, which generates a powerful, permanent, built-in electric field. Think of it as a one-way street for charge. Now, when a photon of sunlight strikes the cell, it knocks an electron loose. Without guidance, that electron would quickly fall back into place, its energy wasted as heat. But the built-in field acts like a slide, instantly whisking the electron away before it can recombine. The channeled flow of countless electrons is electricity. That's power. This elegant process has allowed silicon panel to adorn rooftops and stretch across deserts, monuments to our progress. Their efficiency has steadily climbed from under 10% to over 23% in real-world conditions, and they are famously durable, often guaranteed for 25 years or more. But silicon has a theoretical ceiling, a maximum efficiency it can't surpass, and its physical nature creates other problems. The high purity, brittle wafers make panels heavy and rigid, adding to installation costs and limiting where they can go. You can't easily wrap them around a curved skyscraper or integrate them into a backpack. Worse, silicon is fundamentally wasteful with high energy light. It can't fully capture the energy from blue and ultraviolet photons, instead turning that extra power into useless heat. It's a solid king, but an imperfect one. For decades, the solar story seemed written in silicon, a tale of massive factories and immense heat. But just when the plot felt settled, a new challenger appeared. It wasn't forged in a giant furnace, but synthesized on a simple lab bench. No extreme temperatures, no industrial scale vacuums, no decades of heavy industry. The result is a peculiar crystal structure, almost tailor-made to capture sunlight, perovskite, and it could change everything we thought we knew about solar power. Its rise has been meteoric. In just over a decade, lab efficiencies have skyrocketed, rivaling silicon that took half a century to perfect. Imagine that performance at a fraction of the manufacturing cost. Because perovskites can be made into a liquid, they are lightweight, flexible, and printable, solar as ink. This means solar power could be integrated directly into windows, building facades, or even clothing. We can even tune their chemical recipe to absorb specific colors of light, making them semi-transparent. This opens up possibilities like power generating windows you can still see through. It represents a fundamental shift from the brute force of high temperature physics to the elegant finesse of low-temperature chemistry. But what exactly a perovskite? It's not one single substance, but a versatile crystal blueprint, a structural family of materials. The basic recipe is known as ABX3. Picture a cube, an A ingredient at the corners, a B at the center, and an X on each face. This elegant lattice repeats perfectly in 3D. The magic is that we can swap different atoms into these A, B, and X positions. Today's solar perovskites are synthetic crystals using this principle. One star recipe uses methylammonium for A, lead for B, and halides like iodine for X. The resulting compound is a remarkable semiconductor you can form from a simple liquid solution at room temperature. You can paint it, print it, or spin coat it onto a surface. Then, as the solvent evaporates, the atoms spontaneously arrange themselves into that perfect light-catching crystal structure. Chemistry and physics do all the hard work cheaply on glass or flexible plastics, a new portal to the sun. In perovskites, converting light to electricity is a delicate, efficient dance. A photon excites the crystal, creating an exciton, a partnered electron and hole. In many materials, they quickly recombine. Perovskites are different. Their excitons are weakly bound. Room temperature vibrations are enough to split them. Charges move freely, traveling long distances without getting trapped. The perovskite sits between an electron transport layer and a hole transport layer, one-way streets for charges. Electrons go one way, holes the other, guided and kept apart. They flow through your circuit, do useful work, then meet again to complete the loop, billions of times per second. Rapid separation and smooth transport underpin perovskites' striking efficiencies. With few obstacles, carriers zip through to the electrodes. A little crystal design unlocks big performance. Side by side, the differences are stark. Single junction perovskites now run neck and neck with silicon past 25%. Stack perovskite on silicon and you beat silicon's theoretical limit, over 33% in labs. Perovskites can be solution processed and printed, slashing cost per watt. They're thin, light, and pliable, going places silicon can't. But silicon owns proven durability. 25, 30 plus years and bankable. Durability is perovskite's Achilles heel. Easy to form bonds can break down with moisture, heat, and oxygen. Bad news for outdoor life. Scientists are fighting back with robust encapsulation, glass, advanced polymers, and better chemistries. Lead content raises environmental questions. Encapsulation and recycling protocols aim to keep it contained. Teams are exploring lead-free alternatives with tin and bismuth. Scaling from champion lab cells to large uniform modules is hard. Tiny defects can tank performance. Solve stability, toxicity, and manufacturability. And perovskites pass their final exam. The future of solar hangs in the balance. Despite challenges, real-world trials are here. Labs and startups scaling beyond tiny cells. Pilot lines in the UK, Poland, and China are refining manufacturing. Early markets, tandem cells, an upgrade, not a replacement. Add a perovskite top cell and push standard panels to 28-30% efficiency. Field tests prove performance in real weather. Lightweight, flexible, semi-transparent films unlock niches silicon can't touch. Integrated on high-altitude drones for multi-day flights, surveillance and telecoms, tinted glass-like windows that quietly generate electricity, power-weaving textiles for relief tents and wearables. Even vehicle roofs can harvest the sun. Now imagine the challenges solved. Solar so cheap it's ubiquitous. Energy generated everywhere by everyone. Transforming health, education, and opportunity. Buildings shimmer with transparent cells. Canopies charge EVs. Coatings turn surfaces into power. Jackets trickle charge phones as you walk. Lighter solar keeps drones aloft and connects remote communities. Curiosity-driven science found elegance in a crystal and a revolution in the making.